take it away, introduce your panel, and let's talk hypersonics.
Great. First, thank you for inviting me to be a part of this panel as a moderator. I'm very pleased to introduce three very distinguished panel members today. And I'll just get right into it so we can get started. First, we have Mrs. Long Davis. She's worked at NASA for 32 years at NASA Glenn. She received her bachelor's and master's degrees in mechanical engineering from the University of Akron. She was hired as a research engineer in 1989. She served as project manager in support of the Aeronautics Research Mission Directorate. She's also served as the chief of the Inlet Nozzle Branch, and she is currently serving as the deputy project manager for NASA's Hypersonic Technology Project, and she's been in this role since August of 2020. Ms. Long Davis has also received NASA's Outstanding Leadership Medal, NASA's Exceptional Achievement Medal, the Glenn Federal Women's Program Award for contributions to the advancement of women, and an AIAA Special Service Award. So a very decorated person. Thank you for joining us, Ms. Long. Our second speaker today will be Dr. Eric Marino. Dr. Marino is currently the program officer for hypersonics at the Office of Naval Research, Aviation, Force Projection, and Integrated Defense Department, where he manages fundamental research investments at 6.1 and 6.2 and hypersonic air thermodynamics, high-speed propulsion, high-temperature materials. He's also worked as a chief technologist at AEDC, a hypervelocity wind tunnel 9. He's also worked at Kubrick, and in those positions, he's developed new high-frequency instruments and non-intrusive laser diagnostics for tests on large-scale wind tunnel articles to improve understanding and modeling of hypersonic boundary layer transition, turbulent boundary layers, and shock wave turbulent boundary layer interactions. Dr. Marino has authored or co-authored over 60 conference and journal papers, and he is associate fellow of AIAA, I believe. And so with all of that, Eric, thank you for joining the panel as well. Our third speaker is General retired David L. Stringer, who is director of the Plumbrook Station in Sandusky, Ohio. It's part of the Cleveland NASA Glenn Research Center in Cleveland. He synchronizes activities at this installation to support critical research and development for NASA. He retired from the United States Air Force in 2007 as a brigadier general. He holds a Bachelor of Science in Foreign Service from Georgetown University and a Master of Arts in History from the University of Alabama. He was one of 12 selected annually in the Department of Defense to attend Harvard's John F. Kennedy School of Governance as a National Security Fellow. And I forgot to mention, thank you, General Stringer, for joining us. And I forgot to mention that Dr. Marino received his PhD from Virginia Tech in that introduction. So with that, I'm going to turn the microphone over to Mrs. Long Davis to start us off with a presentation, and we'll kick off the panel discussion. Over.
Thank you, Dr. Bowersox. Can everyone hear me? Does Dr. Bowersox is not? Yeah, okay. Waiting for my charts to come up there. While that's coming up, just again, thank you, Dr. Bowersox, for the introduction, and thank you for the opportunity to be on the panel this morning. I'm not seeing my charts.
Okay, Mary Jo, we're just having a slight technical difficulty. We'll work it.
Okay.
Hang on.
Okay, I'll hold.
That's making me feel a lot better about my technical difficulty.
Yeah. Okay, there you go. All right, so the goal of my presentation today is to give you kind of a bird's eye view of the Hypersonic Technology Project and touch on how our project is contributing to the topic of the panel today, accelerating hypersonics development. Next slide, please. So hypersonics means, different things depending on, kind of where you live and work. There are, shown on this slide, there are kind of four different flavors of hypersonics depending on your interest. There's the blunt body reentry type of hypersonics. There's launch hypersonics. And then there's unpowered atmospheric flight that entails hypersonic gliders. And then that last category there of powered atmospheric flight is really where our hypersonic technology project lives. And we are a part of the Aeronautics Research Mission Directorate, and we're looking there at air breathing powered atmospheric flight. We recognize that it's important for our activity to focus on that powered atmospheric flight, but we are, also maintain connection and apply the expertise that we have in our project when it's called upon to those other areas that require a mastery of hypersonic flight. Next slide. Okay, the Hypersonic Technology Project is focused on reusable applications. So again, the emphasis here is on reusable. And this slide shows kind of three classes of powered atmospheric flight. The first category on the left is weapons, and those are being developed, kind of as we speak, and those are more near-term applications. The middle section of the slide is looking at sustained atmospheric cruise, and that's more midterm kind of applications, and that can be further broken down into commercial point-to-point, which is a civil application, and then on the military side, they look at things like long-range strike and penetrating ISRs. On the far right of the chart is the more farther term powered atmospheric application for space access. And there are both civil and military missions for space access as well. The partnership between NASA and DoD across all of these types of atmospheric flight is critical to maintain progress and U.S. supremacy in the speed regime. Next slide. So the Hypersonic Technology Project actually was restarted in FY17. If you're familiar with hypersonics at all, you kind of know it comes and goes in NASA, and we were able to restart it again in FY17. And the project's vision has really not changed since it came back. Our vision is to enable routine, reusable, air-breathing hypersonic flight. The project is, the approach that we're following here is to conduct fundamental research. We're really focused on the fundamental type technologies, looking to enable a broad spectrum of hypersonic systems like we talked about on that other slide, looking to advance our core capabilities, people, tools, facilities, as well as critical technologies that really kind of set the stage and underpin that mastery of hypersonic flight, all the while looking to ensure U.S. supremacy in hypersonics. There are a lot of international entities working in this arena, and we want to make sure that we stay ahead of them. The scope of our project involves this fundamental research using system level design, analysis, and validation of those critical technologies, again, looking to enable reusable systems. The last bullet there in terms of our scope, and it's probably one of the most important things that I think we do, is to engage, invigorate, and train the next generation of engineers. And we do that in close partnership with universities to make sure that we are supporting their interests, and their interests are being used by our researchers as well. So one of the issues that we find when we're working to invigorate that next generation of engineers is with the ups and downs that we sometimes experience in our funding, it causes a disruption to our students. So the fact that we've been able to have a stable project for quite a while here has helped us to kind of feed that pipeline again, at least do our part within NASA to feed that pipeline again of that next generation of engineers. Next slide. Okay, just wanted to give you a taste of what kind of technologies we're talking about that NASA is investing in. And we make these decisions based on things like, what are our capabilities, what facilities do we have to do this kind of research, and the interests of our workforce. The portfolio is divided into kind of 4 basic investment areas shown here. The system level design, analysis, and validation is that upper left. And kind of the cornerstone of that activity is the uncertainty quantification methodology development that we are working on. Right below that is the area of propulsion technologies. And the cornerstone for that activity is looking at combined cycle mode transition, when you're trying to switch from one engine cycle to another engine cycle and do that smoothly without any disruption to your vehicle performance. Up in the top right is the vehicle technology area. And that investment area probably would be better named like aerothermodynamics. We're looking here and investing in things like boundary layer transition and shockwave boundary layer interaction, trying to understand those kind of phenomena to help us, better control those and model and predict that. And then lastly, but extremely important, are the high temperature and durable materials investment that we make. And this area encompasses things like CMCs, looking at trying to apply CMC technologies to heat exchangers. Critically important are the high temperature seals that are going to be required for any application. And then we're also looking at advanced alloys and using those in additive manufacturing processes to create, complex shapes with intricate cooling, features that you can't necessarily do quite as easily with conventional manufacturing approaches. So that's, like I said, that gives you kind of a taste of the technologies that we're talking about and able to fund within our portfolio. Next slide. So our panel today, we're here to talk about getting there faster, accelerating hypersonics development. And when I saw that topic, I kind of took a step back and gave some thought to that. How is our hypersonic technology project doing this, and what does that look like for us? And I outlined here just some kind of top level bullet points to illustrate how we are helping to accelerate the hypersonics development. Number one, we're collaborating with a wide spectrum of government, industry, and academia partners. And that close collaboration, just working day to day, week to week, if you will, directly on these same projects, that speeds up the knowledge transfer from our folks to the other folks and back and forth. So you don't have to wait for a paper to come out. You are talking and engaging and thinking and solving problems together in real time. And that also directly impacts the stakeholder needs. If they can see what we're working on and they can have a hand in how we kind of guide our research and make suggestions along the way, that helps to accelerate the development. The second bullet is our approach to developing and applying this kind of 3-legged stool approach of modeling and simulation, plus ground testing, plus flight testing. If you can couple those things together, that will speed up the technology maturation, especially if we can get to the point where we have confidence in our modeling and simulation such that we can cut down on the amount of time and the number of tests that it takes in our ground testing activities and our flight testing activities. So it kind of takes all 3 legs of that stool to hopefully speed up the technology maturation and get it out to the user faster. The fourth bullet is our activities where, like I mentioned before, we are developing and validating uncertainty quantification methodology. And we use modeling and simulation all the time. And the question comes back, well, how good is your answer? How good is your prediction? And we need to put some rigor into making that number. And it needs to be a process and a methodology that can be used by every analyst, not just somebody who specializes in applied statistics. It needs to be repeatable, and kind of user-proof. So we are working to develop those uncertainty quantification methodologies. And then lastly we're supporting the development of dual use technology. And by dual use, I mean both civil and military applications. And that just comes down to the fact that if you have more people buying your pieces parts, then it helps establish that supply chain and makes those suppliers healthy. They've got a good customer base and they can stand up and be successful more quickly is the idea. So those are the things that came to my mind as I thought through this topic, and we'll dig a little bit into some of these in the next slides. Next slide, please. This slide is just illustrating or highlighting, emphasizing the importance of our collaborations with DoD. We call this our money bags chart. You can see the money bags on the slide there. Flight tests, no surprise, are very expensive, and those are funded typically by the DoD. And we bring our subject matter experts and our capabilities to the table there to help support that in any way we can. Those are great opportunities for our new engineers to get kind of hands-on experience with that kind of a complex endeavor. And it provides validation data back to the levels below it in the form for the ground testing activities, which both NASA and DoD can afford to fund both of those kinds of things. And we do collaborate on those ground test activities using facilities across the country. And again, that provides more data down to help shore up our modeling and simulation tools, which those activities are not as expensive as the testing activities, but they are critically important, and they rely on all of the test activities to feed their validation and verification. So that collaboration is, again, extremely important for NASA to be successful in our mission. And I'd like to think that those collaborations are, important as well from DoD's perspective. Next slide. Just wanted to kind of highlight some information in the news, if you will, to point to the broader interest in high-speed transports. Recently, the Presidential and Executive Airlift Directorate in the Air Force has awarded 3 contracts to Exosonic, Boom, Supersonic, and Hermeus, looking basically to develop a supersonic Air Force One, which is really cool. And we are looking to partner with them in any way that we can within the Advanced Air Vehicles program to try to leverage what they're doing, in terms of potential testing they might do, and bring the expertise within NASA to bear on this application here. And then on the right, recently, I think it was last month, there were headlines about United Airlines striking an agreement with Boom Supersonic for Mach 1.7 supersonic vehicles. So high-speed transports, they are out there. People are kind of swirling around. There's a lot of interest, and I think the contributions that NASA can make are critical to setting the U.S. up to be a leader in this area. Next slide. So in summary, I hope I've impressed upon you that we're making investments aligned with dual use civil applications. We're addressing challenges in the systems analysis and uncertainty quantification, propulsion technologies, and do fundamental research like I described in aerothermodynamics and materials. And we're strongly leveraging those partnerships across the board with DoD and our partners in academia. And again, our tagline, we're working to enable routine, reusable air-breathing hypersonic flight. And with that, I'm finished, and thank you for your attention.
Great, Mary Jo, thank you for that. That was a fantastic presentation. I have a few questions written down already based on that. Our next presenter this morning is Dr. Eric Marino from ONR. Eric, the screen is yours.
All right, thank you. All right, so happy to be here this morning. Thank you for the introduction. I'll provide a brief overview of the Hypersonics program at ONR that I'm managing. Some focus on aerothermodynamics and instrumentation diagnostic. I'll provide some technical example of some of the work that we're doing. If we go to the next slide, please. All right, so I'll start with the program vision and describing the different research area that we're supporting. So essentially, the program is focusing on fundamental research, and one objective, obviously, is to create new fundamental knowledge. But we can also develop computational, experimental, and flight testing capabilities to support the RDT&E of hypersonic weapon systems. And one major focus, and I'll emphasize that in a few slides, is the workforce. There's hypersonic is an area that's been growing recently, and there's challenges in workforce. So that's a high priority for the program, and I'll talk a little bit about that. The program is quite broad. If you look on the right hand side here, I don't think you can see my the pointer, but that's okay. So area 1-2 is what we could call aerothermodynamics, hypersonics, aerothermodynamics, where we study hypersonic boundary layer, shock boundary interaction. That's really what drives the e-transfer and the sizing of the thermal protection system, aeroacoustic loads, and the aerodynamic performance of the vehicle. To make progress in these areas, we need to validate the tools, increase the understanding of the flow physics, and that requires test facility instrumentation and diagnostics. So that's area 3. One big focus has been the development of predictive tool for performance of those weapon systems, including unique aspects of hypersonics, such as non-continuum, non-equilibrium effects, and aerothermal servoelastics effects. That means essentially if you have a structure that's heating up at a high rate that could deform and then interacts with the flow field, and you want to actuate that surface. So that's quite a lot of things to model, and that would be called multi-physics type simulation. When we operate those systems, one thing that's quite unique, I have to focus on unique aspect, is the Navy. We're not interested, in contrary to what was shown by NASA and reusable system, we don't have the platform to support that type of operation, but we have very challenging demands as far as the scale of the vehicle that we can support on our launch platform, whether the VLS tube or tactical airplane. So volumetric efficiency is a big factor for the design here. It's a big driver, but we're talking about expandable systems. One major challenge for employment of weapon systems, especially if you're looking at systems that are launched at sea level, is the interaction with the environment. And that could be, for instance, oxidation, but also weather interaction. So if you can think about flight through weather, so we have some basic research in that area. Program also has a high-speed propulsion activities. Again, that goes back to size constraints, volumetric efficiency. Propulsion efficiency is extremely important. And here we're looking at air breathing propulsion, as much higher IS speed and rocket or solid booster based system. And there's a big focus on solid fuel propulsion. Last area is ultra high temperature materials that are shape stable. That's a big focus. Ultra high temperature ceramic, for instance. I won't talk too much about that. So I'll focus mostly on 1, 2, and 3 today for the presentation. So if we go to the next slide. I mentioned focus on the workforce. So about 5 years ago, Navy started recognizing that workforce would be a problem with the emphasis on hypersonics, and we've been growing the program since then. We're supporting roughly 75 graduate students at multiple universities. I forgot the exact number. We have about 50 different projects with universities, and that trend is going to keep, at least for 22, it looks like it's probably going to grow a little bit. We've been leveraging multi-university research initiative, which is a DoD-wide program. So we have 2 that are currently active on the effect of weather on hypersonic flight, one on turbulence chemistry interaction, and another one that's going to start next year on ionization to predict electrons and the high enthalpy flows at non-equilibrium flows. So if we go to the next slide. Along with students, right, that's not enough. Obviously, the university, they have to have the research infrastructure to make cutting edge research. So there's the JURIC program that can provide such type of equipment, and we, roughly $1 million per year plus investment in hypersonics in different universities. So you can see some example here. ArcJet facility, University of Texas, Arlington, both upgrading the facility and providing unique laser diagnostics that I'm going to describe. The University of Texas A&M, which is a unique facility, an expansion tunnel to produce very short duration, but very clean, high-speed flow, high enthalpy flow with chemical reaction, where you can study the effect of non-equilibrium on turbulence, for instance. The focus on solid fuel scramjet that I mentioned earlier, we funded 2 facilities at Purdue. One facility is a slab burner, so that provides a unique environment to have an optically accessible combustor, where we can make very detailed measurements of species, temperature, and flame structures and so forth for validating and modeling of combustion process and high speed or in solid fuel ramjet system, which is quite challenging. And laser diagnostics, obviously, pulse burst lasers are unique tools, so there's quite a lot of new laser system that have been deployed at different universities. So if we go to the next slide. I'll talk briefly about bond error transition. So why we care about that? Well, obviously, e-transfer increased by up to 5 to 10 times when you have transition or turbulent flow versus transitional. Fully turbulent flow is not necessarily the worst case. Transitional can be worse, especially on controlled surfaces. And there's been a lot of progress in tools developed at universities, direct numerical simulation, when you can resolve all the turbulence length scale. There's an example here of actually a quiet DNS, where you're looking at those vortices that's on the bottom left, and very good agreement with experiments. So experimental validation is obviously key, but then you can introduce disturbances, that's the image on the bottom, and look at the instabilities and how those go to turbulence. DNS is very expensive, so there's additional tools that are not as expensive, but that can be validated against DNS, and IO is one of those tools where you're looking at the equation as a linear, in that case, it's a linearized Navier-Stokes equation as a linear system with inputs and outputs, and figuring out which input maximizes the output. And on the bottom right here, you can see very good agreement with experiments. And in that case, you have streaks that are generated in shock binary interaction, and that can lead to turbulence. So that's all great. Well, we have great tools at university, but if users in the DoD are not using these tools, then there's very limited impact on systems. So we're working with APL to actually further mature and validate those tools and applying them for the first time on actual weapon system geometry. And some of the benefit, obviously, is if you have an existing system, you understand better the performance, then you can have more aggressive, for instance, flight envelopes and so forth. And a big focus as well is boundary error is no longer perceived as a random process, but we understand the instabilities. And once you do that, actually, you can optimize your vehicle shape. Very minor changes can delay transition. And you can also implement control strategies. So we have research in that area that I won't have time to go through more details here, but let's go to the next slide. The next slide is going to talk about turbulent flow. So eventually, depending on the altitude, if you're at lower altitude, you'll get a turbulent boundary layer. And it's quite challenging to make prediction of e-transfer in some cases. You can be up to a factor of 2 off with ground test data. And direct numerical simulation here offers a unique opportunity to fully assess the different terms that would be driving the turbulence. And here we also have a leveraging development from university. We have a project with APL, a frontier project which provides hundreds of millions of CPU hours, and we can do DNS on relevant weapon system geometry, and that's never been done before. And then validate validate these things, these computation against measurements or flight data that's available. I won't go into much detail, but if you can see on the bottom here, we can actually achieve quite sizable Reynolds number, altitude, for instance, the Kubrick data here, and make good progress in RANS modeling, Reynolds average Navier-Stokes modeling with the very high fidelity simulation. If we go to the next slide. I've talked early on about the instrumentation and diagnostics. I'll go into a little bit more details, but what we can do in test facilities, right, really depend on what you can measure. You might have a great facility, but if you cannot measure the relevant quantities, the utility is a little bit limited. So on the left here, you have the ArcJet facility at University of Texas Arlington. On the right, the Texas A&M facilities. And the bottom line is there's no single facility that can replicate all the aspects of hypersonic flight. So you really need to have a different set of facilities for different aspects. For instance, the one on the left here would be good for material testing, but the flow field might not be as clean, so not so good for doing fundamental study of aerothermochemistry, whereas the facility on the right there would be very good for that, but with the short test time, not suitable for material testing. Next slide. Diagnostics is like I said, a big deal. There's been a lot of progress. If you click one more time, there should be some animation. Just one more click. All right, so PIV, right, where we put particles in the flow, that's sort of the go-to method, well suited for supersonic flow. And hypersonic flow, the particles don't follow the flow well enough to enable that measurement technique at high Mach number. So if you go to the next slide. So we need to figure out other ways, and one way to do that is actually, instead of tracking molecules, or instead of tracking particles, you actually track molecules in the flow. And one example is the krypton tagging velocimetry that actually was developed by Stephen University's Professor Parziali in collaboration with ADC when I used to work there, and that's been shown to work actually in Tunnel 9 and also in smaller scale facilities. And right now we're pushing that technique to get very high rep rate and get time resolve, fully resolved turbulence measurements. But that's been a good story over the last 7 years or so. And more recently, actually, it's been used in Caltech facility at high enthalpy. So that's a unique environment where that method's been successful. If we go to the next slide. So we're funding various methods for measuring different things with leading experts. Dick Miles at Texas A&M looking at measuring electron number, density, and temperatures. We work with Ron Ensign with a new technique called spectrally resolved LIF, where we can measure actually temperature, pressure, atomic species, and high enthalpy flows. I've talked about the krypton tagging velocimetry, so we're pushing these techniques to higher rep rate with pulse burst lasers. And the last thing I'm going to show on diagnostics is the ArcJet characterization that we're doing. And all these techniques can be transitioned to large-scale T&E facility because they don't use any particles. The krypton can be seeded successfully in most facilities, such as Tunnel 9. But the big advantage of these techniques is there's no particle seeding. Next slide. That one shows an example of the measurements at the UTA facility. That was the first time that the free stream was directly measured in an ArcJet facility with molecular tagging. And it's quite simple. If you look at the top line here that's moving, you know the initial position of the line, and then after a small delta t, the line is moving, and then you can get the velocity. And the line is created by dissociating the nitrogen in the flow. And when it recombines, it glows in the red, and that's what you can image on the camera. You can see quite a lot of turbulence for that condition, and that had to do with some issues with the vacuum system for that Mach number. At other conditions, there was less turbulence, but that's an interesting thing, an important thing to measure because it can affect heat transfer, the turbulence. And we can also measure the what's in the flow field with those techniques. Next slide. All right, so I'm going to conclude here. as far as the topic of the day, really, there's currently a major gap in predictive capabilities for computational tools for hypersonics, and that's impeding the development of weapon system. You can always do brute force approach where you do a lot of component testing, ground testing, and that works, but that's not the most efficient. You might not get optimal design for that. So we're really pushing hard on predictive tools and diagnostics to actually validate those tools in relevant environments. Workforce is a big deal at the moment. And then we also work with other organizations. I should probably add NASA here. Actually, we've been able to use some of our university performers have been able to use NASA facilities, University of Maryland, University of UTSI, University of Tennessee Space Institute, and we work closely with FOSR, AGSI, and OSDRME. So I'm going to conclude here. Thank you for your attention.
Great, Eric. Thank you for that presentation. A lot of work going on there. All very relevant to what we're talking about today. Okay, last but certainly not least in terms of presentations is retired General Stringer. General Stringer, the floor is yours.
Thanks a lot, Rodney. And you know, folks, my presentation is going to look like a skateboard brought to an F-35 fly-off. So Mary Jo Long-Davis and Eric Marino are the F-35 pilots, and so I'm the skateboard operator. So let's talk, as Eric had said, no one facility does it all. So what are the advantages? So my assertion here is that 7 or 8 years ago, we were about a 3-year backlog in ground test facilities dealing with hypersonics. So that means that as the programs of record have burgeoned, we have an even more pressing need for ground test. Why do you ground test? To rule out bad ideas. For scaling and other integration factors, you're not necessarily going to get it all right, but that's what you want to do. The advantage of ground testing is, at least in theory, you can be more secure than you would be if you flew it. One of the crying needs, it seems to me, is sensor and communications development, especially for atmospheric flight, because communicating in and out of plasma is a real challenge. Sensor effects in and out of plasma are another real challenge, and you're trying to figure out how you can make that work. There is a possibility to communicate through plasma. Researcher in Glenn Research Center's communications area has posited that that could be true. He's done bell jar experiments, but he's never been able to do something bigger. The other thing I'd suggest is that we have to use tools, but we're doing them partially on faith without data points, because you need a lot of data points. Science, as we know, is repeatable results. So you want as many data points as possible. To show you how that works for you, let's look at store separation in subsonic areas where the Air Force cut its flight testing by 90%. How could they do this? Because with millions of data points, both in flight and in wind tunnel testing, it's now customary to use a 4-foot wind tunnel at Arnold Engineering Development Center, run the stores through that. They do simple verification of the edges of the envelope in the air, and you're good. But that, again, is with millions of data points. As you know, transonic and the kind of high-speed supersonic or hypersonic we're talking about, we are very short of data points. So as Mary Jo Long-Davis showed, one informs the other. Flight capacity is one thing that's been a problem, obviously, because airspace is a problem, because you don't want to put people at risk. One of the difficulties is if your idea is to shoot it into the Pacific and let it go into the drink, then you don't have the asset to look at. So it might be worth some idea of looking at asset recovery as a part of the flight test program. Something as crude as a parachute recovery, or even getting the entry point in the ocean to be at a continental shelf or in some disused area. I'm thinking something like Point Mugu to Alaska might be useful for us to consider. Again, you're looking at repeatability, because ultimately we don't want things that are incompletely tested or not tested at all. Because what happens is America especially depends on its technical excellence to offset its inferiority in the numbers of people that it has. And every time that we have a system that doesn't work, we invite our adversaries to believe that none of our systems work. That's not true, but we put our people at risk when we don't do that. We can also consider the nice part is we've refreshed ourselves with the Operation Warp Speed for the COVID vaccine on the Defense Production Act of '54, which also was mirrored on the World War II industrial mobilization experience. If we want to, we can look at the menu of test facilities and laboratories we want to operate, centrally fund them, and then sequence them. That's at least a possibility for us to consider if we wanted to. Finally, not on the slide, but my colleagues talked about it, people. I think it's very important, and I salute the efforts that Office of Naval Research has done and others have done. We need U.S. citizen engineers and technicians with clearances to work on our programs. And I think if you worked on a real program, whether you were in a VOTEC program or an engineering school, you'd be getting experience that's valuable to both you and the nation. And I will salute our colleagues, Joe Jewell, Tom Giuliano, and Brian Schmidt, working from Purdue, Notre Dame, and Case respectively, to think about ways to get folks to do this better. I know there's time for questions. I'll pick up my skateboard and walk back and see if I can help Mary Jo and Eric refuel their F-35s. So back to you, Rodney.
Great. Thank you, General Stringer. So this is the Q&A discussion part of the panel. And as questions are coming in, Jim is going to moderate the questions as they come in. But I have a few to maybe help kick us off, if that's okay. So first, when we talk about workforce development, and I think there was all three of you spoke to workforce development. And in a current role that I'm with DoD in terms of the University Consortium for Applied Hypersonics, workforce development is a big area, and we have a big thrust working through this. But one of the questions that comes to my mind over and over and over again is how do we best define the demand signal across vocational versus technical versus, so that we can help inform the universities and our technical schools to prepare people for this workforce need that we see coming. So as you're developing your programs at ONR, for example, or you're developing, you're identifying your workforce needs at NASA, do you think those transition similarly to the industry? Or is industry fighting the same fight that you're fighting, or is there a different fight that they're fighting? I'd like to hear your input on how we can best inform the universities and the technical schools on the demand signal. Over. That's to anyone who wants to chime in.
I can chime in on that one, right? As far as ONR, it's not only the new workforce, but also workforce and workforce center. That's an aspect that with funding research in those areas, and then also have students aware of those workforce center because they're funded by the Navy. It's not exactly the answer to your exact question, but that's also, and also workforce at universities. So we're funding heavily young researcher. General Stringer mentioned Joe Jewell, so he's a FY21 YIP awardee, Young Investigator Program awardee from ONR. I think, right, the programs like FOSR and ONR are probably going to be developing more specialized, and I think previously they were called almost like the Navy SEALs of research or something like that, right? Like the highly technical, but there's going to be a whole array of expertise. But I think most people right now working in hypersonic probably have a master's degree. So that's probably a sort of entry, right, to get the specialized, if you're doing engineering, obviously technicians and all the other trades, that's also important. But at ONR, I think and FOSR is probably more the highly specialized, and not only in industry, but academia, right? You need to train the next generation of master's students and so forth. So that's my perspective on it, but I'm happy to hear what the others have to say.
Great, thank you.
Yeah, I would just add to that your comment about the vocational workforce development, that's an interesting perspective to bring up, because I think on the NASA side, obviously we have a highly skilled technician workforce, but I think industry may have a larger need for that, and so I don't know that we are cultivating as many, that as hard as the industry needs on the NASA side. So I think we're definitely the expertise in the engineering field and master's and PhD. I think we're doing our part there, but on the vocational side, we may not be the pull that industry would be looking for. That's a really important point, though.
So let me also suggest, Rodney, that if I agree with my colleague's statements, and from a demand signal standpoint, it's really actually easy. If the government invests in a security clearance for a U.S. citizen technician or engineer and provides that technician or engineer actual experience, then she or he already has a wonderful opportunity to go to government or industry, and regardless of flavor, because it would certainly make an attractive candidate for Eric or Mary Jo to hire if you've got that kind of experience. So I think that's how you create the demand signal. And here's the good news. You don't have to work on the same thing all the time, but much like Elon Musk wants to hire university graduates who actually worked in hands-on competitions to do something, kind of the MIT model, this would be a great way to say, wow, you want to be part of that program, because you will have an asset after you've done it that makes you enormously attractive.
Oh, great answer.
Rodney, if I could jump in real quick. I mean, that's, I had formulated a question about that, energizing these, the college students to, and even just building just general awareness of this field. There's rocketry competitions, there's aviation kind of competitions. I mean, you can't realistically have a hypersonic competition. So how do you get them aware of and interested in that particular segment, without being able to have those types of things? What is there to get them going? Tours of facilities, just going to schools and talking to it? What is it?
Jim, I can fill in. I'm happy to answer some of that. One thing I was hoping to talk about, and I guess I didn't. In my previous role, we had at ADC, working very closely with the University of Maryland, where we had actually undergrad doing interns in the facility. And then that evolved into a program where we could actually have students doing their PhD and doing testing in the Tunnel 9 facility, a unique facility. And then they could get, eventually clearances, and, some of them ended up in various places like APL, AFRL. So that's one way to get them quite early. And they were honor students usually in the aerospace engineering department. So I think expanding that, there's a lot of value there. So that's one way I think to get them, and other outreach activities, right, with high school students, and we did some of that as well. So I'll let the others chime in.
So Jim, we work extensively with our local VOTEC and more outlying VOTECs to get kids interested when we can. COVID has obviously put a stop to that, in the same way that NASA internships for high schoolers and college students have been virtual the past 2 cycles. But I think those are very valuable ways to do it. At our place, one of the other things I would suggest to anybody watching is when tours are able to be safely done, you can always show off what you do. And our people love to talk about what they do. And it's a way of exciting people who might be inclined to do this. And I think that's enormously important, whether you're government or industry or a college or a university or a VOTEC, you can always show people what you're doing. Isn't this cool? Yes, it is. And I would simply underline again, Jim, if I knew I had a program where I could get a clearance and actual experience, and I was inclined to put my hands on equipment, either engineer or technician, I know you'll get people to sign up for
it. I guess my 2-word answer is we need to fly more. I hear it all the time that people in this field, we love airplanes, we love propulsion systems, and we want to see hardware, and we want to be part of something flying. So I think that energizes everybody in this community.
So if you don't mind me, Jim, just following up on Mary Jo's comment, that was my follow-up question too, is why aren't we flying more, and why aren't we flying more with universities, and how can we engage universities in sounding rocketry tests? We're doing some of this with the Air Force right now. You showed some graphics on that, working with Scott Berry and Chuck Leonard and of course Sarah Popkin at AFOSR. So the question is, why aren't we doing, how can we do more of this? Can we synergize to provide these opportunities? And I think we could do a senior design competition in hypersonics, and maybe it could culminate in a flight test that could be very useful. I mean, there's ways to be innovative. And I'm stealing that idea. I'm working for the consortium, and a lot of very creative people are contacting me about ways to engage. And that was one of the ideas that came out of TCU, for example, who doesn't have a graduate program, but they have a really strong undergraduate program. And so integrating, coming up with a sort of a senior design competition. So my question is, can we do that? And if not, what if we can, what's holding us back besides funding? I know funding is always a thing, but besides funding, what's holding us back?
Rodney, let me suggest a how. Our colleagues at Wallops Flight Facility do sounding rockets.
Yep.
And as you know, that's a perfect place to test shapes, this, that, and the other, to fly a senior design competition, track it, get data back, et cetera. So that's a capability that's standing by that simply needs a funding line. So there's a way to do that. And Dave Pierce, who runs Wallops, I haven't talked to him about this specific idea, but I think he would be very receptive, and it's something that might get some attention. I'll defer to Mary Jo and Eric on their ideas.
There's I think we also need to think about innovative way besides sounding rockets, and those could be subscale projectile light gas gun type, yep, which is not quite flight test, but is a good way between the traditional ground test and flight, and also for developing instrumentation and sensors. And for reentry, actually, there's CubeSat. I think that's been explored as well for the very high enthalpy flows with chemical reactions. So I think sounding rockets are great, but also I think the cost would go down if we had every year, right, a given number of flight, and then people compete maybe to get the ride on, and then with a more standardized architecture that we can build reliability. So because right now I think, right, it's sort of you flip a coin, and whether or not it's going to work is probably right, whether which side you're going to hit on, and that's probably not good enough. And usually you have one flight, right, for the budget. So I think having a repeatable sequence of flights, and then by technical merit, right, you write proposals and then you can get the ride. I think that would make a lot of sense.
Almost like a CubeSat kind of revolution, but for hypersonic vehicles, like like you said, standardized bus, to put them on, and it goes off, and like maybe Virgin Galactic's airborne launch thing or something like that.
Yeah, there's opportunities there as well with the private sector.
Yeah.
So, yep.
Mary Jo, did you have something else?
Yeah, I was just gonna kind of tag on to Eric's comment there that it shouldn't be such a holiday or such an event when we have these flights. It should be, more routine, kind of, so that we get used to doing them, and it's not so hard each time. They're not so new each time. So
yeah, I would follow on with that and just say that would make us a little less risk averse, because I think right now, if we have a failure and it's a one-off, it's a major disaster. But if it's 1 of 10 that fails, that's completely acceptable.
So with the time we have left, if I may, Rodney, theme for this event, for the overall Glenn Symposium, has been convergence. So what I wanted to ask was, what have we learned? What can we learn from spaceflight vehicles in their reentry phase, that might apply to hypersonics. How can we use that going forward? Like the, Sierra Nevada, the Dream Chaser, things like that. I guess it's the X-37B, or are we learning anything from that when it re-enters? And on the flip side, what have we or can we learn from supersonic aircraft, back when Concorde was flying, and the SR-71 too, but as we, vehicles like that and the upcoming programs, what can we learn from that might apply to the hypersonic realm? Like you talked earlier before about comms and plasma. Is that something that can be tested on re-entry of a vehicle that might be applied to hypersonics? So I'll pause there and open that up.
Well, re-entry vehicle typically would have different trajectory and different aerodynamic or aerothermal characteristic, usually blunter shapes, right? So we were trying to decelerate, whereas a DoD vehicle usually would glide for a prolonged period. So that creates challenges in the environment. But there might be some of the commercial space access. I forgot which one in particular, where you could launch things from a large airplane, for instance, and go through those more relevant trajectories than the ballistic trajectory or re-entry trajectory, typical re-entry trajectory. And the range of Mach number is usually lower than what NASA is interested in for Earth. Well, not NASA Hypersonics, but NASA, right? EDL type applications. So entry, descent, landing. So.
Right.
Jim, I think it's possible to entry, descent, landing, blunt body, figure 4 minutes, calm out. So if you're able to try communicating through plasma at that point and make it work, it doesn't solve your 30 to 60 minute problem necessarily, but it sure does get you started.
Okay. Okay, then we're just about out of time, so let's go around the table. Lightning round question, 10-15 second answer each. I'll start with you, Mary Jo. What's keeping you up at night? What about this is the biggest thing in your head?
I think, from most recently, we've been considering commercial applications and commercial hypersonic transport possibilities.
We didn't get to that. Yeah,
that's okay, but it's not keeping me up at night. I guess I'm sort of excited about it, and so I think about it a lot. But how do we deal with those challenges? How do we make a vehicle like that sustainable from the beginning? Addressing the environmental and certification challenges. I think that's a fun, exciting thing to get to work that could be something the normal person flies on in the future.
Got it. Eric, how about you?
I would say probably technology transition. How do we take with the good stuff that we start at universities and then, get them transition and have an impact for the warfighter? So, I think we have good ways to do that, but that's always a challenge, right? And usually there's a down select process along the way and not everything works, which is fine. We take risks. But I think you could always do a better job at having an impact on the actual warfighter. So that's probably the main thing.
Gotcha. David?
Test capacity, mobilization, flight and ground. We don't have enough. We need to do more. We're operating at the speed of routine. We need to really ramp it up if we're going to make this happen. Particularly disadvantaged are the Army and Navy.
Is that a national security concern?
Well, it's a concern for all of us because we need more opportunities to learn lessons and get insight. The purpose of testing is knowledge. So we need to test. Here's the other good news, Jim. You can call it a lab or you can call it a test facility. The lab or facility doesn't care how you use it. Once you have a capability, it can be used for anything that's suitable.
Right. Makes sense. Rodney, what about you?
Okay, for me, I think we're at a really great point in time where the opportunities to make advancements are there. The support is there, and I really hope that we can coordinate ourselves in a way to really fully utilize and capitalize on this opportunity to make a difference, not only for access to and from space, but for national defense and maybe even commercial airlines. So I do think there's a great opportunity in front of us, and we need to seize this moment.
Excellent. All right. Well, everybody, thank you so much. Again, we do this again. We're an hour in, and we could probably go another hour. No, it was a great conversation. Thank you so much for everything. We really appreciate it. And so with that, we're now going to, we've eaten to the lunch break by a couple of minutes, but that's okay. So we're going to take a break for a little while. We'll come back at 1:10 p.m. Eastern, and we'll present our second of our AAS Molly K. McCauley Awards. So thank you very much to all of you, and we'll see everybody else back here in about 25 minutes. Thanks.